continue. So we had this discussion in the last class about tree-level amplitudes in string theory. The last class we computed 4-point functions. We got this nice formula in terms of ratios of gamma functions, and we discussed how these 4-point functions have singularities correspond to exchange of particles. We discussed how unitarity allowed us to determine the prefactor that appeared behind every particular vertex operator in terms of this unknown determinant of the sphere, and we discussed how this prefactor is the same as that the relative ratios of these prefactors is the same as that you would get by the state operator map. We didn't work that out in class, but I urged you to try to work that out.
You made a comment about the finiteness of students.
Yes. Good. So we also talked about the high energy behavior of string scattering amplitudes, and one of the things that we found was that if you did high energy fixed angle scattering, you've got some 4 particles, they do something here, and then they come out. K1, K2, K3, K4. K1, K2, K3, K4 are all taken to be large in the sense of high energy. So high energy, high spectral momentum, they come in and go out at some fixed angle. Okay? Now, when this happens, we found that the amplitude went like e to the power minus alpha prime s log s plus the same expressions with T. Okay? The point to notice here is that this amplitude is exponentially smaller at high energies. Even more than exponentially smaller at high energies. Okay, now this you have to contrast with the behavior of tree-level scattering of gravitons. We did this calculation for tacticals, but though it's more work, you could do the same kind of calculation for the scattering of 4 gravitons. Okay? And you get the same kind of result. Okay? So the point is the following. If you did a 4-point scattering amplitude calculation for gravitons in Einstein gravity, the result, instead of decaying at high energies, would blow up at high energies. Why is that? It's just because the effective gravitational coupling constant has powers of the energy in the numerator. You see, the gravity theory is a 2-derivative theory. Every interaction occurs with 2 derivatives. Okay? So with every interaction vertex you have 2 powers of k. So in this net diagram you have 4 powers of k, and the whole thing will blow up. Will become very large at high energies. Okay? So this result is very different from the result that you get in gravity. This is connected to the finiteness of string theory for the following reason. You see, you have all kinds of ultraviolet divergences in doing the gravity part of the diagram. The ultraviolet divergences, of course, come from the fact that very high energy gravitons running in loops give you very large contributions. However, here you're seeing that any vertex factor involving very large energies is very small. The kind of divergences you get from high energies running in loops is powers of divergences, right? From final diagrams. However, the kind of suppressions we're getting from amplitudes are exponential. Okay? So suppose you've got some process in which you've got some loop running around here, and you have very high energies at these loop momenta. Okay? Then this is proportional to some apparent divergence, but you have multiplied by the effective vertex factors. Okay? And these effective vertex factors, as we've just seen, are becoming very small. So that's the key point. It's just that the scattering amplitudes die off at very high energies. And therefore, everything, that's connected to the fact that everything at high energies is stable. Okay? And they die off exponentially.
Does it change the statement that the gravitational coupling constant, you would expect it to run in a certain way, right?
Yeah, no, it doesn't change that. You see, the exponential comes, but it would not be there if you just had graviton, scattered to graviton. That part still naively grows. It's just a classical calculation, so that part grows according to the classical gravitational technology. Okay?
So what cancels that?
What cancels it is everything else running in these points. You see, it's not just the exchange of graviton you have to look at. You have to look at the exchange of all string states. And the whole thing is exponentially small. Now, said this way, it sounds like a miracle. However, there's another way to say it, which makes it sound less miraculous. You see? And the other way to say it is that, well, look, what is the size of a string state? Okay? So, any string state has size approximately alpha, right? Okay? Now, when you scan, okay. So suppose you had an electron and was sent to scatter against some big fluffy cloud of positive charge. How will the scattering go? Well, the scattering amplitude is proportional in the Ball approximation. Suppose you set it in the amplitude k by 1. Right? In the Ball approximation, scattering amplitude is proportional to the Fourier transform of the source function and momentum k minus k prime. Okay? Now, if k minus k prime is very large compared to the length scale in the charge distribution, that Fourier transform is very small. Okay? What I say is e to the power minus I kx times minus x squared by 2, let's say a squared. So A is the size. What is that equal to? Let's do the Gaussian integral here. So we get something that's proportional to e to the power minus k squared a squared by 2. So if k is very small, this is an exponentially small amplitude. Is this clear? Sorry, if k is very large, this is an exponentially small amplitude. If your momentum is very small, if the wavelength of your particle is very small compared to the size of the object you're scattering against, this is a divided by wavelength. Okay? This kind of smallness is a name, sometimes called a form factor. It tells you that if you scatter at very high energies, very small wavelengths, you scatter off something that's very big. Such scattering is always very small. As we've just seen, it's a property of Fourier transformation. Okay? So, what's going on here is that let's go to a frame in which we've got two strings coming together. Let's go into a frame in which one of them is at rest and the other one's coming hard at it. So one that's at rest is like this guy in some object of string scale size against which these things collide. Okay? Now, if you go to energies much higher than string scale, so that the wavelength associated with the projectile is much smaller than the string scale, then we're exactly in the situation. The guy that's colliding is colliding off a big fluffy cloud of size string scale, but it's got much smaller wavelength, and we get exponential separation basically this form factor. Okay? That's basically what's going on here. Is this clear? From this point of view, you also see what's going on. You see, the limit where gravity dominates over everything else, in that limit you can think of the string as a point particle. It's the smallest size state. On the other hand, at very high energies, this thing will excite all kinds of string states equally. It's very misleading to think of the string as a point. In fact, it's a big fluffy cloud. Okay? In which all the excitations up to the energy that's available to you are equally being excited. Okay? So clearly it would be a bad approximation to use just the gravity approximation. The answer? But we've got an exact formula. We know what it does. And this picture gives a much better description of what's going on than gravity's.
maybe you would expect that gravity would dominate over all other interactions, at least the interactions that we feel funny out.
But yeah.
But here what is happening, if I understand right, is that there are new interactions which have been added,
Yes.
which together make it soft.
Exactly. The new interactions are all the other excited string states.
And they are also, like very heavily separate interactions that I can't now be.
The net sum of all of them, you don't separate the interactions. The net effect, the net sum of all of this is very high, is very highly suppressed at high energies. You see, what we've done is not say that we've taken the full 4-point function, full 4-point scattering amplitude, now separated into that part that comes from graviton exchange, and that part that comes from first excited state exchange, and so on. Each of those will be some power. We sum it all up, and then you get this. You get this behavior that happens. Okay? So, more by more, it sounds like a miracle that this happens. But if you think of the object, it's this picture that makes it intuitive.
This is regarding a statement that is it always true that when the gravity dominates over all other interactions, the string length should be smaller?
When I didn't understand the question, saying when gravity dominates over all other interactions.
Say we are working. If we want to work in an approximation where I just have gravity, if I don't want to add any other interaction.
Okay, good.
Then it is necessary that in that my string length in that approximation be small compared to all other things.
That's right. You see, why is that true? It's basically if you want to keep only gravity and B field and dilaton, and ignore everything else, you want to be in an energy regime where producing other particles in intermediate states is suppressed by the energy. And that will be the case when your energies are smaller than the lightest other state that exists. The lightest other state that exists has mass of order 1 over the square root alpha prime. So long as you are at energies that are much smaller than 1 over the square root alpha prime, gravity and the other masses interactions are. Okay? And only when that happens will that say. Okay? So this is just Wilsonian. If you want gravity to dominate, you have to be an energy smaller than the other lightest mass. Good. Other questions, comments?
Just one small clarification. This the bond approximation that you use is hydrogen.
Yes.
And it's not strictly valid, right? This is but the correction to that.
It's not extreme quantum. We're doing tree-level scattering. We're doing basically classical string theory. Anything that's tree-level is essentially classical.
Right.
There's no powers of H constant.
Right.
Okay? There are many things about this approximation one could criticize. I think the way I wrote it was not very interesting. So, but the appropriate version of that thing, would apply to this. Once we start thinking about loops, we're not doing classical. We have to make.
And those the loop corrections will of course be subdominant. That's why
It's suppressed by G string, but the question, the kind of question that makes that issue tricky in field theory is that formal suppression by G string an artifact is a number that multiplies at infinity. And we get divergence in field theory, and that often causes the naive perturbation expansion to be a value. Okay, so we will see that's not the case in string theory. There is, everything's completely well behaved, completely finite. This is our first indication of that statement. Had the sign been the other one, it would basically have been impossible to get finite perturbation. Here it is.
We never had to go beyond 3-level string theory to get this kind of a gravity.
Correct.
So
this kind of high energy suppression.
High energy suppression.
Yeah.
So what is happily, I mean, like in the sense that we would expect that the gravity would get surprised by some kind of. Okay, there is a distinction on what is classical and quantum in gravity and what is classical and quantum in strings.
Right.
So, I mean, how do you really quantify it? As in, how come we just did T-level scattering and
all we're doing is treating. We not use loops at all. Well, what we're finding is that the exchange of the graviton is cancelled by the exchange of all other particles. Look, let's see how that works in the final formulas. I'm going to ask somebody to help me get the formulas right. Give me the product for gamma. It was gamma of A, gamma of B, gamma of C divided by gamma of 1 minus A, 1 minus B, 1 minus C. Okay, so it's A, B, gamma C over gamma of 1 minus A, gamma of 1 minus B, gamma of 1 minus C. Okay, now somebody help me with what A, B, C were.
A was
minus 1 plus S by 4 and then T U B. Okay. A, B and C are these things. Good. Now, how do we see that gravity scattering goes with energy from this format? Okay? To do that, what we have to do is to work into the graviton pole. We did this last time. Okay? We saw that when we sat at the graviton pole, we got contributions that were proportional, remember, to k to the 4. We got contributions that were proportional to k to the 4, which is like t squared or something. T plus 1 squared. T. Some polynomial in t squared. T plus constant squared.
We consider the pole at equal to 0.
Right.
By graviton you mean all?
All masses, yes. Graviton, B, mu, dilaton. Just by sitting on the pole, we can't distinguish them. But if we want, we would have to do more careful experiments. Keep track of polarization dependence and so on. But at this level, that's all masses. Okay. Now, let's look at the structure of the poles more carefully at higher and higher excited levels. Okay, just to see how the amplitudes grow with energy and at different excited levels. Fine. So let's go and sit at the pole. Remember, we said A equals 0 was the capital. A is equal to 1 minus 1 was the graviton. Okay, so let's go instead to A equals minus n. Let's go to A equals minus n and see if we can understand what the residue of this pole looks like. Okay, so we remember we had A plus B plus C is equal to 1. Okay, we're setting A is equal to minus n. Let's use B as our variable. So we get C is equal to 1 plus n minus n. Okay, so we have A equals minus n. That gives us some sort of pole here with some n factorial which I will read about. Okay, now we have to put in what all these other things. Okay, so this thing is 1 plus n factorial. 1 plus n gamma, which is n factorial. This thing has a pole times some other factorials. Ignore. So these guys are different. They look different. So this is gamma of b times gamma of 1 plus n minus b over gamma of 1 minus b times gamma of 1 minus 1 minus b minus. Okay? So the residue of the pole is this ratio of gamma functions. Now, let's compute about this ratio of gamma functions. We do that by using this property of gamma functions that tells us that gamma of b is b minus 1 times gamma of b minus 1 and so on. Go all the way down to b minus n. So that cancels that with the product of b minus 1 into b minus 2 up to b minus n. Okay? Similarly, here, so which is the larger, so similarly this guy is the larger one, yeah? So once again we get factors up to 1 minus b, and the first factor we get is n minus b. So it's all the same factors occurring with the minus, the other way around. So what are we getting? We're getting b minus 1 squared, b minus 2 squared, up to b minus n of b squared. Okay? If we're at very high energy, so that b is much larger than 1 to 3 up to n. Okay? This is just b to the power 2. B, remember, is something like T. Okay? So each of these exchanges grows like some power of energy. You got a higher and higher orders in the mass level being exchanged, you get higher and higher powers of energy in the vertices. Okay? So you might think, well, we've set ourselves up here for a huge blow. Gravity goes up like k to the 4th, next guy goes up like k to the 8th, and oh my god, it's going to be terrible. However, that's not true. Look at the high energy limit of the exact answer. It's an exponential. All we are seeing, if we go to very high energies, is that if you take, something like e to the power minus x squared, and you data expand it, it looks like x squared plus x to the 4th plus x to the 6th and so on. And you say, oh my, so this must mean that when x becomes very large, we're in deep trouble because we're getting x to very high powers. That's nonsense. All we had is e to the power minus x squared. Okay? So, that's the situation with, the exchange of everything is classical. The exchange of higher and higher mass levels gives you higher and higher powers of x. So it's not true that the graviton exchange dominates the high energies. The other things are certainly important, in fact more important in this formal way, but they all sum up into something very small. As you see explicitly from the formula.
So if I understand correctly, now you want to make a statement further into a quantum.
It was meant to be a throwaway intuitive statement that will be justified by loop calculations.
Right. So since the vertex contributions are exponential, then if you consider quantum loops, is that correct?
Yeah.
That will be
the effect, you see, something running in a loop, if it's very large, has to connect with the rest of the diagram.
right.
That connection factor will be exponentially increased. So will lead to very small contributions from that. Now, such arguments have many ways of going wrong. So you should trust such arguments. It just gives you, these are words that gives you a way of thinking or a way of remembering and visualizing something once they're confirmed by the formulas. Okay? So this is not a substitute for doing loop calculations at all. It's just have some way of thinking.
But this is a very unusual thing if you think of it in terms of field theory. You just put a lot of non-renormalizing interactions.
Yes, you're very unusual from the world of field theory. That's why string theory is so special. It's not like string theory is some any old Lagrangian that you deal with. You see, as we will see as we go on, that string theory is very tightly constrained. For instance, if you take a field theory without gravity, you can often change it in the UV without changing much. Okay? For instance, you take a theory and you had one cutoff. You change the cutoff to something else. You take dimensional regularization to something else. Okay, maybe some parameters of the energies change a little bit, but you see, one of the things that we discussed when we were discussing the consistency of string theory amplitudes, you remember, was that Bianchi invariance of string theory required that was true only up to total derivatives in moduli space. Do you remember that? if you looked at the expression of the string amplitude, there was an integral of a moduli space, and then there was you got some total derivatives. Now, as we will see, the integral of a moduli space corresponds to the loop integral of field theory. We'll see that in this lecture. So we'll discuss the loop element. You will see that. Okay, so if changing the cutoff is like adding some factor to the loop amplitude. Okay, if you change a propagate from every time something flows very large with k, you put a theta function there. Put an e to the power minus k squared. Okay? So changing how you do that integral is the cutoff of field theory. If you want to do anything other than what string theory asks you to do, you will not decouple the RST in that instance. If you were just to take the moduli space integral, just cut it off somewhere. Say, oh, I won't integrate over averages. Like we often do it. That will ruin the gauge invariance of string theory. Because you will get surface terms to this BRS. So null states won't decouple anymore. Theory won't make any sense. It won't be unitary. Okay? So as we will see more and more as we go along, string theory is not any old quantum field theory. In particular, certainly nobody's understood how to take string theory effective action and change it a little bit and still get consistent theory. It's not that kind of theory. It's very tightly constrained from its internal structure. So, from the point of view of theory, this looks like a miracle. From that point of view, it does look like a miracle. But it happens because the field theory point of view is an effective description that's valid in a certain regime. But when you go high energies, that's very valid. So many different parts. Other questions about this? Okay, great. So let's continue. Actually, something I don't remember if I said it in detail, but you may remember we computed 3-point graviton scattering, and we got an answer that had various powers of k in it. I just wanted us to remark that it's only the lowest orders in the powers of k that comes from the Einstein equation. Higher orders in k come from derivative corrections to the gravity vector action. As we will see as we go along, these higher order corrections are very different in the superstring theory. Okay, this is a remark I don't think I made a way to explain this. Okay, fine. Any other questions about classical tree-level string scattering before we turn to data loop? Great. Let's move on. Okay, so today we're going to study the simplest non-tree level kind of amplitudes that we get in string theory, and these will be amplitudes on the torus, amplitudes in genus 1. Okay, so the first thing we're going to do is to study the torus in just as geometrical manifold to the extent we need it. Okay, so first, what is a torus? So, one can think of torus, in coordinates in which the metric has been made, is y equivalent to something that's flat. Okay? So one can think of the torus as a metric as, well, the metric ds squared is equal to dw bar, the usual metric, okay, with the identifications w is equal to w plus 1, maybe I should say 2pi. W is equal to W plus 2pi, and W is equal to W plus 2 pi W. Okay? So think of the complex W plane. So we've got some complex W plane. And on this complex W plane, you draw two lattice vectors. The first one is in the real axis direction and it's got length 2 pi. And the second one is in some complex direction, whatever it is. And this vector is the complex number 2 pi. Okay? Now, you can take the whole of the complex plane and break it up into fundamental regions, each of which is related to this little parallelogram by these identifications. Okay? So anything here, anything anywhere in the complex plane can be pulled inside this parallelogram by using these identifications input times. Okay? So, this is what the torus is. It's this strip of the complex plane, this little region of the complex plane. But remember that according to identifications, this side and this side are identified, and this side and this side are identified. Okay? So if you want to think of it pictorially, while this is in general an arbitrary complex number, let's think first of a rectangular torus. Okay? So identifying this side and this side gives you a cylinder. You see that? Because this becomes a circle times a line. And then identifying this end and this end identifies the ends of the cylinder, so closest number. Okay? So we got the torus. The torus as you visualize it. It is clear. Okay. Now, the first question we're going to ask is, suppose we've got a tori with different values of this identification parameter tau. Okay? Are these different tori in fact while and diffeomorphism equivalent objects? Or equivalent here, are they conformally related? Are they conformally related to each other? Okay? So, the answer is going to be in general no. Okay? The answer is going to be in general no. But in order to see that, let's try to do a calculation. This calculation will be useful for us taking on this one. Okay, so suppose we've got two different tori. Okay, one which is this object, and another one which is w prime is equal to w prime plus 2 pi, and w prime is equal to w prime plus 2 pi. Okay, and now what I'm going to do is to make a coordinate change in w prime. In both of these two tori are different. In this, the metric is d square is equal to d w prime d w prime bar. Okay, so now what I'm going to do is to make a coordinate change in w prime in order that in the new coordinates, I have the same identifications as I did for w. Okay, and then we check whether the two metrics are conformally related. Is this clear? So, what am I going to do? So, I'm going to define w prime is equal to aw plus b w bar. Okay? And I'm going to have these things I'm going to choose a and b such that the identifications of w and w prime coincide. Okay, maybe I should start with yet another variable, z and z bar, just not to confuse these two. Okay, and I'm going to demand that when w prime goes to w prime plus 1, it implies z goes to z plus 1. And w prime goes to w prime plus 2 pi. Sorry, this is plus 1 is always 2 pi. Okay, so and W prime goes to W prime plus 2 pi tau implies Z goes to Z plus 2 pi tau. Tau prime, as I said, goes to Z plus 2 pi 2 pi tau. So we're going to try to change the identification moduli of this torus by a quadrant change. Okay, so let's see what I get for these numbers again.
So we want the W prime bar to be the bar of this.
The W prime bar is the bar of W prime.
I mean, will it be A bar, Z bar?
Yes, A bar, Z bar plus B bar. Okay, so now let's see. So the first condition gives us the equation that A plus B is equal to 1. Because if I set 1 and 1 here, I should get 1. Hello? Sorry. Yeah, so just go ahead and do it for you. Just go ahead. Yeah, sure. No. Okay. Okay, great. Sorry. Okay, so now what about the other guys? Let's move. So for the other guy, we have the equation that tau prime is equal to A tau plus B tau. Okay, we also had A plus B equals 1, so let's write this as 1 minus A. So now we can go ahead and solve. Right, so we find that A is equal to 1 over tau minus tau bar into tau prime minus tau bar.
These are the two conditions that you choose in.
Yes.
You impose.
I impose these conditions so that I change the periodicities appropriately. Okay? And B is equal to 1 minus A is equal to tau minus tau bar sorry, tau minus tau prime over tau minus tau. Okay? Let's check. If we chose tau equals tau prime, we should get B equals 0, so that works. And we should get A equals 1, that also works. Okay, fine. So now we know what, so we know the answer, we know that W prime, which was made, can be rewritten as tau prime minus tau bar times Z plus tau minus tau prime times Z bar over tau minus tau bar. Okay? Now let's take the metric dw prime bar and rewrite it in terms of the Z coordinates. Okay? So we rewrite the metric of W prime in terms of the Z coordinates. What do we get? Well, we get a term that's dz bar, but we also get terms that are dz squared and dz bar squared. Let's write down what the dz squared and dz bar squared is. So the term that's dz squared comes from taking z here and z the other one, that comes from there. Okay, so that would give us tau prime minus tau bar over tau bar minus tau prime bar over tau minus tau bar mod squared times dz squared. Okay, and there would be a similar dz, the complex conjugate of this would be dz bar. So we see that the metric has not changed when we change the identifications. When we change the identifications so as to change tau and tau prime. Once we change identifications, the metric in this new coordinate is not conformally related to this guy. See, these two spaces now, in terms of z and w, we have the same range of coordinates. But different metrics are not just, the metrics are not just different, they're also not conformally related. They're not violated to each other. Is this clear? So while of course it's possible to change the identification range by coordinate transformation, that change changes the metric. That change changes the metric by a factor that's not, in general, a Weyl transformation. So these two different objects are different manifolds as far as up to Weyl and diffeomorphisms are concerned. Is this clear? Okay? So we've got this one complex parameter set of tori, which are distinct complex, distinct conformally inequivalent, which are conformally inequivalent manifolds. And though I'm not going to try to demonstrate it to you. Okay, so this is important because that tells us that for the case of the torus, unlike for the case of the sphere, we now have moduli. Okay? There was one sphere up to conformal transformations. Okay? But there's one complex parameter set of tori. I'm not going to try to demonstrate to you that there is. Well, okay, you can probably demonstrate that there's nothing else where it's okay. Suppose we started with a rectangular torus. Okay? And we asked, what are the moduli fields? Now we know from the equations of motion that the moduli fields, infinitesimally, the number of moduli come from the number of zero modes, the number of zero modes of the field B. In this coordinate system, the zero modes of the field B are simply analytic functions. So we're going to list all analytic functions that respect the periodicity of the torus. There's only one analytic function that respects the periodicity of the torus, namely the constant. So the two complex components of the constant are the two moduli fields. These are the two zero modes of the P operator. These are the two zero modes of the operator. So this is another way of thinking of the moduli. If you think of it in terms of zero modes of P, we just enumerate the zero modes of P. Okay, fine. Just so that we have it in our hands for when we need it in a moment. Let's. I'm going to need to compute what dz squared is in this situation. What dz squared is at first order. At first order in the variation of this complex parameter here. Okay, so at first order, we get delta of tau bar times the factor of I times imaginary part of tau. Okay. So if you computed the change in the dz squared part of the metric, when you do this coordinate change, the change in the metric is delta tau bar times imaginary part of it, divided by imaginary part of tau. You see that, right? I just said this is the place where you get the first order variation. Then everywhere else I said tau prime equals tau. Tau prime minus, so tau minus tau bar is twice I times imaginary. Oh, so the factors of 2 are probably I times imaginary. Okay, that's all I want to say about. Oh, this is one more thing I'm going to say about the tori, but that's all I want to say about the moduli spaces. Oh no, there's one more. Sorry. Let me say one more thing immediately about the moduli spaces. Okay, so you might think that, well, good. So now I understand the moduli space of the tori is labeled by one complex value to tau. However, that is wrong. That is not a complete description of the moduli space of tori. Okay, how do you see? Why is it wrong? Can somebody tell me why it's wrong? So let's look at this picture. We have a complex plane, and one of our identifications is always along here. Let's say we have one torus which had its identification along here. Now, can somebody suggest another set of identifications that will give me actually the same physical space? I'm claiming that there are discrete identifications in the space of time. That there's discrete equivalences in the space of time. See, you identify with w goes to w plus 2 pi and w goes to w plus 2 pi tau. That is the same thing as doing some other identification. Any suggestions for what? Arrow down meaning? That's good. Okay, good. So the first thing is that tau goes to minus tau. It's symmetric. That's correct. But anything else? Like there's an extra half space. Well, suppose w is equal to w plus.
Oh, okay. So minus 2 would also be yours.
What? Say.
So if this is tau and you take
Very good. Very good. This guy. You see, because this guy is the same point as this guy. Same point as this guy, that implies the same point as this guy. You can get to this guy by shifting here and here. So what I'm saying is that suppose you have w is equal to w plus 2 pi, w is equal to w plus 2 pi tau, then we can add these two equations. You can add n times this equation plus this equation, and you'll find that w is equal to w plus 2 pi, and w is equal to w plus 2 pi into tau plus n. These two are completely equivalent to each other. Because to get back to this system, you can take this equation and subtract n times. Is this clear? So there's a statement that we've identified things modulo tau, that to start with one integer worth of ambiguity. Okay. Tau goes to tau plus n does not define a new space. Okay? What we think of as the basic cycles of the torus change. For instance, if you now go to tau plus 1, you think of this is the basic cycle of that torus. These two are the basic cycles. And this is a complicated, composite of this guy and this guy. Okay, so what? Your basic cycles of the torus change, but that's your choice of description. The space itself hasn't changed.
Okay, they are not made.
These two are simply the same space.
Yes, but okay, so but it's not obvious from this expression of the metric.
From this expression of the metric? No, it's not obvious. So that's a good question. You can take all of these different tori and write them in a space where the identifications are 2 pi this way and 2 pi this way. Okay? And then you could ask, well, now suppose when you do that, you get complicated matrix, as we say. Okay? Now you can ask, now I take two different spaces with one with tau and the other with tau plus n, and are these two things equivalent? And you can show this a coordinate change that relates these to each other without changing in this case, without any wild factor and without changing the identifications. What kind of coordinate change is that? The coordinate change is of the form. So suppose you take sigma 1, sigma 2. it's a coordinate change of form A, B, C, D, where A, B, C, D are all integers, and the determinant of A, B, C, D is equal to 1. In this particular case, it's a special example of this. The special example being 1, 1, 1. Okay, this particular coordinate change, I'm not going to work it out. Yeah, but this particular coordinate change will change the net. It's manifest since these are all integers, that it's not changing the identifications. Okay, sigma went to sigma plus 2 pi times n. We're just refining with the integer coefficients, it doesn't change the identifications. But the special thing is that what it will do is take the metric with one particular value of tau and rewrite it with another particular value of tau. And this is in the example that we talked about here, 1, n, 0, 1, all coefficients determinant equals 1. This will be tau versus tau plus n.
But this goes back to, we just saw that metric and we just argued that it is not related to that metric by varying. But this is an example that there will be some coordinate change which can make it very equivalent.
No, this is not even while equivalent. In the example we're talking about here, there's no while factor.
Yes, that is true. What I'm saying is that so what does it do for the previous argument?
What was previous argument?
That that the metrics are not very equivalent.
Yes, good. You see, what will go on there will be that it's possible to find a coordinate change. You see, the coordinate change that we tried to do was the following. It tried to keep the fundamental cycles of the two toruses the same. You see, we wanted to work in coordinates such that when we took tau, z goes to z plus tau, we had w goes to w plus tau. In those coordinates, it doesn't work. However, you can try to find another set of coordinates such that when z goes to z plus tau, it's not w goes to w plus tau prime, but w goes to w plus tau prime plus n. So there's another coordinate change which changes which identifications you're looking at. Okay, that does work. But you see, we didn't see in this analysis, firstly because we fixed on what coordinate change we're looking at, but these other coordinate changes are discrete. So infinitesimally what we've done here is completely correct. But it misses the possibility of some big discrete identifications by more imaginative coordinate changes. You understand what I mean? In the algebra that we worked out here, we demanded more than equivalence. We demanded equivalence plus that the two cycles of the tori map to each other. That's too strong a demand. What you should demand is there's some coordinate system in which the two things match. How I know. Is this clear?
Okay, so now it's clear that the tau is actually a modulus.
Oh yes, because infinitesimally what we did was completely different. Okay. The only other ambiguity we had was something. You see, suppose you make a small change, then you can't change this cycle to sum of this cycle plus this cycle, right? Then that would never work. If you make a big change, maybe you can. So infinitesimally, if two tori are infinitesimally related, then the two cycles that must map to each other or not at all. Okay? So this argument is certainly correct infinitesimally, but it leaves open the possibility that there are discrete identifications. Is this clear? Okay? So we certainly got a two-dimensional moduli space. That's what the earlier argument showed us. Okay? But as we've seen already, this two-dimensional moduli space is not the whole complex plane. Just because we didn't try hard enough, with discrete ambiguities to try to fix it. But we're doing that. Okay, we could have been more systematic. We could have approached the whole thing more systematic. Is this clear? Still unhappy? Go on.
Can you just okay? can we do this kind of an identification of going to 2 pi to 2 pi I for a different tau bar where they are not related with this integer? What would they? I mean, if you try to do that, what would happen?
Well, we get different identification. I mean, sorry, I didn't answer the question. Maybe I missed.
Okay. Here the argument was that two different, right, with two different tau and tau bar which differ by an integer.
Tau prime. So yeah.
So tau and tau prime which differ by an integer.
Yes.
Actually can be seen to be the same.
Yes.
As well going into this 2 pi and 2 pi.
Exactly. It's manifest from one description of the problem. It's clear that that's true. Yes, go.
Okay. Now, is there some way of arguing that it is?
That there's no other identification.
It's just that it's not very that these two are not okay. This is right. This is I accept that these two are the same space.
Yes.
Okay. What I'm not convinced about is that the previous argument that they are not made equal, because I thought that like previously that this was some canonical coordinate transformation and we see that they are not made equal and so they are not made equal. But here what is happening is that there will be some other coordinate ambiguities which may do in this argument and it's not
okay. Firstly, I want to convince you that if two different taus are related infinitesimally, are very near to each other, then the only possible way in which it could work is the kind of coordinate transformation we tried. Okay, see, because what are the possibilities? Okay, maybe I can tell you how we get back to this, but maybe I can tell you how you can systematically approach this. Okay, one way of systematically approaching this is taking these different tori and switching it all to the same space. Okay, so it's a space with identifications 2 pi, 2 pi. You get two different metrics. I mean, you get a metric that depends on tau. Okay, now your identification is not going to allow yourself to fool around. Okay, now you can ask what kind of coordinate changes can you make that respect these identifications. Okay, and that will basically be identifications of this sort. These things we mentioned. Now you can just do that identification. And remember, these are integers. Okay? So you can't make something that's infinitesimally different. Okay? So, otherwise that becomes the identification. Now you can just do this identification and see what it does to tau.
okay.
And that will give you the full class of things that we thought were different but actually the same. Okay, that will be a systematic way to approach it. Is this clear? It's so clear that from that point of view, that this thing would be parameterized by these matrices with integers.
If I understand correctly, then I think the possibility that there could be some other identifications also that is not exhausted.
We've not yet exhausted, not from what I've said. From what I just told Longnagel, that would exhaust everything when you did that exercise. We're getting to the full exhaustion.
That can be proved.
It can be proved, and in fact, it's more or less proved. Okay, certainly in this exercise that. See, this is not all of this. You spend 10 minutes to prove it. I mean, it's not no deep anything. Okay. Other questions, comments? Fine. So, but everyone agrees that there was this discrete identification. Okay. Now I want to ask you that up to Weyl transformations, can you think of any other discrete identifications? Okay. Let's start. Let's start with the rectangular. course. Okay. Suppose we had this is 2 pi and this is 2 pi I times some a. So tau is I times a. Okay. Now I'm claiming that if you took tau to minus 1 by tau, Suppose you had another rectangular torus in which the tau was equal to I by A. Now let's look at a torus in which tau is equal to minus I divided by A, minus of 1 by IA, which is equal to I by A. I'm telling that these two tori are one.
You put the minus sign behind.
The minus sign is in my definition. Yes? Okay? So I'm telling you that these two tori are one. How do I say that? I say that by saying that, well, you see, in this space here, let me write this in sigma 1, sigma 2. Okay, so the metric here is d sigma 1 squared plus d sigma 2 squared. Something squared is dz dz. But the identification ranges are sigma 1 is equal to sigma 1 plus 2 pi, and sigma 2 is equal to sigma 2 plus 2 pi into by 8. Okay? Now, let me put out a factor of 1 by A squared. So let me write this as sigma 2 by A the whole thing squared by sigma 1 by A the whole thing squared with factor of A squared. Now, after while transformation, the overall factors don't matter. Okay? So this is d sigma 1 tilde squared plus d sigma 2 tilde squared, where sigma 1 tilde is equal to sigma 1 by A, and so has identification sigma 1 tilde plus 2 pi. I wanted A. So sigma 1 tilde is sigma 1 tilde is sigma 1 by A, sigma 1 A, same with sigma 2. Okay, so we have sigma 1 tilde is equal to sigma 1 tilde plus 2 pi A, and sigma 2 tilde is equal to sigma 2 tilde plus 2 pi. Now I switch my labels. I switch what I call 1 and 2. And I got exactly this torus. Because this torus had sigma 1 plus 2 pi, and sigma 2 is sigma 2 plus 2 pi A. Okay? So, at least for the rectangular torus, you see that the map tau is equal to tau goes to tau minus 1 by tau. Okay? Actually gives you the same torus. What's going on here is very simple to understand geometry. Suppose you had a long torus like this. You flip it around. And then you rescale such that this long edge becomes 2 pi. This edge then becomes very small. That's the A goes to 1 by A. So what's happening is the xy flip. You change what you regard as the x-axis and the y-axis, and then rescale everything so the x-axis has identification 1. So those are our conventions. Okay? So if the x-axis was originally, if the y-axis was originally very, y identification was originally very long, once you flip and contract, the new y-axis will be short. By this A goes to 1. Okay? So this operation of tau goes to tau plus 1. Okay, I'm going to leave you to check that more generally speaking, more generally than for a rectangular torus, for any kind of torus, tau goes to minus 1 by tau is always an equivalence. Okay, but the right one will change. Okay, so this identification here, these two identifications are related. This one is sometimes called T. This tau goes to tau plus 1. Sometimes given the name T, well this tau goes to minus 1 over tau is sometimes given the name S. Okay. Now, if you have tau goes to tau plus 1, tau plus n, and you have tau goes to minus 1 by tau, you can compound these two. So you can think of these two as generators, elements of a group. generators of a group, and the full group is whatever you get when you close both, all operations that you can make by combining any arbitrary set of these. So let's see what you get. So what do you get? You get tau goes to A tau plus B over C tau plus D. Okay. That where A, B, C, D are all integers, and A, B, C, D, this determinant okay, first let's just say that in order to convince you of this, I'll tell you about two facts. Well, first let's say that the two operations that we looked at were this one. Okay? Tau goes to tau plus 1 is what? It's the matrix 1, 0, 0, 1. Right? Because tau goes to tau plus 1, so A should be 1, D should be 1, B should be 1. C should be 0. So this is a matrix with determinant 1, all integer coefficients. Okay? Next, what about tau goes to minus 1 by tau? So tau goes to minus 1 by tau would be the matrix A0, D0, and let's say B equals minus 1, C equals 1. Okay? So once again, this is a matrix whose entries are integers. Okay? But whose entries are integers and whose determinant is 1. Now, the next thing you can check is the following. Suppose you compound two of these transformations. You had a tau goes to A tau plus B plus C tau plus D. And then you have another, so tau prime was equal to, let's say tau double prime was equal to this with tau prime, and then tau prime itself was equal to A tau plus B over C tau plus D. Then you can ask, what is the net transformation that's generated by this operation? And you'll find it's of the same form. So I'll leave this for you to check. You'll find it's of the same form with the new matrices of A, B, C, and D being the product in the matrix sense of the other two matrices. Is that clear? So you've got the first transformation generated by one matrix, the second transformation generated by a second matrix. If you compound transformations, that is matrix multiplications for these matrices. Okay? So what we're dealing with here is a group, some subgroup of the set of 2 cross 2 matrices. Okay? Now, what can we say about the subgroup? It's clear that if you take something of this form and multiply it with something of this form, so you always start with integers, you always end up with integers. It's some set differences of integers. Okay? So the entries of the group will always be integers. Moreover, since the determinant, the product of determinants of matrices, the determinant of a product of matrices is the product of determinant of matrices. The fact that both these generated elements have determinant equals 1 will mean that what you're left with is determinant equals 1. Okay, so clearly you're going to have integer entries and determinant equal to 1. And you can also convince yourself that every such element, every such matrix with integer entries and determinant equal to 1 can be generated by taking sufficient, by taking powers of these two guys. Okay? This is the full group. And it has a name, it's called SN2 set. Okay? Okay? The S here means determinant equals 1, Z means integer entries, 2 cross 2 matrices with determinant equals 1 and integer entries. Okay, great. So, now we understand better what the moduli space of tori is. It's the space of all taus modulo SL2Z. Modulo SL2Z transformations of tau. Again, modulo, there's the space of all taus, and then there's an SL2Z identification that acts on taus according to this formula. Okay, and the space of inequivalent tori are given by sets of taus that are not related to each other by an SL2Z transformation. Is this clear? Now let's try to understand in some sort of geometrical, let's try to draw a picture of the set of inequivalent taus. Okay, so let's draw the tau plane. Now, we know that tau goes to tau plus 1 is an identification. So clearly, we can always take any tau and put it to lie between minus half and half. Okay. Also, from Jyotirmoy's initial observation, we don't have to worry about this bottom side. Because when you identify like that is the same thing. Okay, so clearly everything, just by using tau goes to minus tau and a negativity set of flip, we're only interested in the top half of this diagram. But we can do better. Because you see that suppose something was down. Okay, now let's see what tau goes to 1 by tau does to us. Tau goes to minus 1 by tau. You see, when you take tau goes to minus 1 by tau, in particular what you're doing to the modulus of tau is inverting it. So let's draw the circle of modulus of tau equals 1. The circle which is mod tau equals 1. Okay? Suppose you have something here. If you act on it with tau goes to minus 1 by tau, you get something with modulus of tau greater. Now, either this could be here or it could be outside. Okay. Now, if it was outside, you can once again use tau plus 1 to bring it inside. Now, this when you do this operation will either end up here or be some other point here. But basically, you can show, though I've never tried to do it myself, but though I'm sure it's not difficult, you can show that this process can always be isolated so that in the end you end up at some point outside here. Okay? So clearly, the fundamental domain on the space of taus is the space between minus half and half and exterior to the unit circle. Okay, that any tau in this plane can be brought to a tau of that form by an SL2Z transformation. Okay, now of course there are many other fundamental domains of the space. For instance, what you can do is take this fundamental domain and see what it maps to under tau goes to minus 1 by tau. Okay, it maps to something like this. That's another fundamental domain of this, of our space, and there's an infinite number of them. Okay, but when doing string theory, we'll have to do an integral over all moduli. So we'll be doing an integral over all inequivalent tori. We'll pick some fundamental domain. The domain we will usually concentrate on is this guy. Okay, that's all I want to say about the moduli of tori. Any questions or comments? Great. Fine. So now that we've understood moduli of tori in great detail, let's turn to the conformal Killing vectors. So once we get the question about conformal Killing vectors, the question about conformal Killing vectors is the question of how many 0 modes of the of that P operator acting on C up there. Okay. Now, once again, in this coordinate system, everything is analytic. That operator simply del Z bar. So we're looking for analytic vector fields that respect the identifications of the torus. So these vector fields are given by Z. At the basis of these vector fields is Z to the power n times del Z. But n has to be equal to 0 if it's going to respect the identifications of the torus. Okay? So the number of conformal Gilling vectors once again is 2. This del Z and del Z bar. One analytic, one anti-analytic. It's the same as the number of moduli. Right. So CPA fields. Okay, let's check that this matches everything that. Let's check that this matches everything we know about the surface from general considerations. You remember that there's a Riemann-Roch theorem that we had. This theorem that came from counting zero, that came from the anomaly of the BC system. It told us, well, in this case, it's actually very easy to remember the result. Because you remember that the number of B insertions minus the number of C insertions was fixed to be a certain number because of the anomaly. But you remember the anomaly is proportional to the scalar curvature on the one sheet of the string. Now on the torus, the scalar curvature can be chosen to be 0. So the integral of the scalar curvature is 0. So in this case, there's no anomaly. There's no integrated anomaly. Okay? So number of B minus number of C modes in order to get non-zero amplitudes, in this case, must be 0. So the number of C0 modes must be equal to the number of B0 modes. And that works beautifully because we found that the number of moduli was 2 or 1 complex, and the number of conformal Gilling vectors was also 2 or 1 complex. Okay, great. So, that's all about general considerations for the torus. Now we want to try and set up string theory of the torus. Are there any questions upon it? Fine. Okay. So now, the complicated part about setting up string amplitudes was to work out a way to get to the ghost insertions. Okay? And when we were working with the sphere, we didn't have to worry about the ghost insertions because about the V insertions because there were no moduli. Now we have two moduli, so we have to figure these out. Okay, so let's remember what the insertion connected with the modulus. The insertion connected with the modulus is d2 sigma times square root g alpha beta, g theta phi, b alpha beta, and del tau, where this is the modulus, times g beta phi. And then there's another factor. Associated with tau bar. Okay. But so suppose we had a torus of a certain modulus, and we changed the tau modulus in the middle. Now this formula assumes that we're not changing coordinate ranges, we're changing metric. That's what's going on here. That's why at the beginning of the class, what we did was to relate the two pictures. It's one picture in which you keep the metric unchanged but change the coordinate ranges. Second picture in which you don't change the coordinate range, but change the metric a bit. Okay? And you remember that we found, okay, now, so suppose we had this guy with identification tau. Suppose we had this guy with identification tau, and we changed tau a little bit. Okay? We had this guy with identification tau, and the metric was dz bar. And we changed tau a little bit. Now, the metric was dz bar, so every undeformed metric here has only dz bar components. So this guy is 1, and this tells you that this is B bzz, which we call B, times del tau of gz bar z bar. Okay? And then you have plus B bar, integral B bar times del tau bar plus, of course, del tau bar z bar. Correctly, sorry. So, first insertion was what? It was this guy. So we had to keep a d tau derivative. So this is d tau of g z bar times b plus b bar times d tau of g z z. Integrated. And this insertion here was integral of b times del tau bar of gz bar z bar plus integral of b bar times del tau of gz bar z bar. Tau bar of gz bar z bar. Okay? Is this clear? These were the two insertion factors that we discussed in our general discussion. Scattering amplitudes, which I just worked out for this case using the fact that ignoring constants in this discussion, using the fact we know what the metric looks like in this place. Now, at the beginning of the class, we worked out that delta of gzz we worked out the delta gzz was equal to delta tau bar over im tau times numbers. Okay, so and delta of gz bar z bar is equal to delta tau over im tau times numbers. Okay, so let's plug in. From here, we get this guy clicking. This guy clicks, and gz bar z gzz. I discuss this first. Zz. And from here, this guy clicks, each of which gives you a factor of 1 by u now. Okay? And so we conclude that the net insertion, the product of these two insertions is a product of 1 by imaginary part of tau times minus. Is this clear? Times, of course, an insertion of times an insertion of integral of b of z times integral of b bar of z bar. B bar. Is this clear? gives us the following. You see, we have to integrate over the metrical moduli space. We have to integrate over moduli space. So we had a d tau bar integral. But the insertion of b's tells us that that's not the only tau dependent. This thing is in fact divided by imaginary part of tau square. Then if you do it really carefully, you also keep track of all numbers. You also keep track of all numbers. I'll give you the final, but when you keep track really all somehow messed up the one power of being tau, which is these final answers go away to tau. Oh, I see what's happening. Yes. Alright, probably that integrates this. Okay, as far as I can see, what we've done so far is correct, but I have to match my formula with Kuczynski, which has one factor. Yeah, I'll clear this up. It's probably like this integral gives you an extra. He writes it in terms of the zero, just an insertion at one point. That integral is the volume of the torus, which probably has an extra factor in tau in numerator, which therefore gives you 1 over u tau instead of 1 over u tau square. But let me not take let me yeah. I think that's probably what's going on. But let me just confirm that carefully next class. Get back to you. Okay, I think written as it's written here, it's correct. There's one more manipulation. Because in the end these B insertions only refer to the zero mode. The zero mode is a constant, as we've seen. So we can actually do this integral with the zero mode, and the net result has just one factor of in tau in the denominator. But let me get back to it. Okay, good. But at the moment we've got these integrals and we've got these things. Fine. So that's one set of that's one set of insertions that we dealt with. Now let's move on to the next set of insertions. Okay, so the next set of insertions are we need to put one vertex operator with a C and another vertex operator with a C the C tilde and have this fixed. Okay. However, once again here, the the only effect of the C insertions is the 0 mode. And we've seen that the C0 mode is constant. It's the conformal killing vector, which is just constant to us. Okay? So the issue of whether this C insertion is fixed, firstly, we don't care about where we fix it. Okay? We don't care about where we fix it, but it's when we fix it, we multiply it by the 0 mode of the conformal killing vector at that point. Okay? But the 0 mode of the conformal killing vector at that point is a constant. Right? So suppose you remember what the general formula was. The insertions from C's give you the determinant of the insertions from C's give you the determinant of Ci sigma j. Right, but Ci's were the two 0 modes in the game, and sigma j was a point insertion. Okay, but so what we so what we get here is times first this right. So that's right. So let's go to complex coordinates. So the two conformal killing vectors are C1z equals 1, C1z bar 0. Okay, and C2z equals 0, C2z bar equals 1. Okay, something purely holomorphic direction or something purely anti-holomorphic direction. Okay, now we should be evaluating these things. In general, these would have been functions of where we were, but in this case, this is just a constant. It's independent of these coordinates, yeah? Okay, so we just get, this determinant of 1, 0, 0, 1. Okay? So the point is that is it